Alright, so we're up to the last lesson in this topic now, the matter stuff. So, emission spectra. So, earlier in the topic talked about that there was energy levels inside an atom. So I use that as a bit of a diagram. So, there are energy levels inside an atom, and there may be an electron might be here. And so if we can somehow give that energy, that electron, we can get it to move up to there. And so if we can get it to move up to there, it's not actually going to want to be there, and it's going to drop back down to where it would like to be. And so they can move between the energy levels if we give them the energy to do so. Now, when it drops back down, we get the energy being released. Alright, because it doesn't want to be in that higher energy level, it wants to be in its normal one. So that energy has got to somehow be released, and it's released in the form of a photon, in other words, light. So you get light out of it. Alright, so it gives off some sort of light, and so it's called emission spectra. Now there's an equation that we can work out here. We don't work it out, but it's been worked out for us, that the energy of the photon will be equal to the energy of the higher level minus the energy of the lower level. Alright, so that all sounds fair enough. Well, we also get then that's then related to the colour of that light, and the colour of the light is related to the frequency, and so the energy of the photon would be hf. Now, h is a thing called Planck's constant after Max Planck. And there's two values of Planck's constant depending on whether we're working in joule for the energy or whether we're working in electron volts. So one of them, the joule one, is 6.626 by 10 to the minus 34, and that's joules seconds. And if we're working in electron volts, it's 4.136 by 10 to the minus 15 electron volts seconds. And so, depending on what you're working in, you choose the appropriate one. Alright, so I mentioned earlier that, briefly, that there was different energy levels for different atoms, and here's an image which depicts for some different atoms. Alright, so here's three here. We've got hydrogen there, we've got mercury here, and then we've got sodium there. And let's just look at the hydrogen one to start with. So the ground state is the normal level. So normally an electron, use a different colour, normally an electron sits there. We can get it, if we give energy, get it to come up there, maybe, and then it might drop back down. And when it drops down, as I said, gives off a photon. So, and then we've got the hydrogen, the mercury in the middle, and then the sodium energy levels, and you can see the numbers next to them are different. Now, another thing I'll point out, see how here we've got negative 13.6 electron volts. Here we've got 0. It's just, for the ground state, it's just two different ways of doing the same thing. So if we need to put 13.6 electron volts in to remove an electron from hydrogen, and if we look over here at the sodium, up the top here, you need to put 5.13 electron volts in to remove an electron from that. A bit easier in the sodium because the sodium's a bigger atom, so the outer shell electron, which is what this ground state is about, is further from the nucleus than it is in the hydrogen, so it's a little bit easier in that respect to move it. Alright, so in the middle one, hydrogen, again they use the negative and then zero ionisation level, so it's when you've completely removed that electron from the atom. Alright, got another diagram. Alright, so here's another one. Again, this is a hydrogen. And so, depending on where we excite this electron here to, depends on what can kind of happen. And so, if I excite it all the way to there, there's a whole thing that can drop just to the next level, it could drop to that level, it could drop all the way to there, or it could drop all the way back down, and that's what all of these, of course, if it drops to this level, then this third excited state, then there's a bunch of ways we can get there. Now, when you have a look at the diagram on the right there, up the corner there, that diagram kind of also depicts the shell area, so those fuzzy round lines are the shells, so it gets excited to here. And then there's all the possibilities shown. So the blue one here, this blue one, relates to this line when it drops from there to there. Alright, and so there's your shell. The green one in the middle there, that's when it drops from there to there. And the red one, the little one at the end there, is when it drops from here to here. Alright, so we can look at those levels and we can work out what the difference in the levels are, and then we can work out frequencies. Alright, so let's have a look at a couple of examples. Okay, first example, it says looking at figure 21.15, so it's back a couple of pages. Alright, so it's this one on the end. And it says, what is the energy of a photon emitted when an atom sodium falls from the 2.1 eV level to the ground state? So the energy of the photon, remember, is the higher minus the lower. And so this one's 210 minus the lower when we go back to the ground state. Whoops, too far. In that hydrogen one, here's our ground state down here, looking at 0. So minus 0, so 2.1 electron volts. Alright, the next one, same deal, the energy of the photon. From the higher, 3.75, to the lower, minus 210, 1.65 electron volts for that one. Alright, let us have a look at the second example. Okay, what is the minimum energy required to ionise a hydrogen atom, figure 21.13 or above? It's above in your notes, but it's back a couple of pages. Here we go, wrong, another page, there we go, here it is. 21.13 to ionise. So the ionisation level, when we've removed that electron, is up here. And so that would be at 0 eV. So that's the higher level. The lower level is this one here, 13.6, negative 13.6 in the way that's done. So energy of the photon is the higher level, 0, minus the lower level, which was negative 13.6, which then is just 13.6 eV. Okay, so then it says, what is the frequency? So frequency, remember, E equals HF, the energy of the photon. So the energy we're looking for is 13.6. Now, because that's in electron volts, we need to choose the electron volt version of Planck's constant. Where are we? We're back again. There it is, 4.136 by 10 to the minus 15. So let's go back. There we are. 4.136 by 10 to the minus 15 times the frequency. So dividing both sides by Planck's constant, you get that the frequency is 3.2 by 10 to the 15, and the unit is hertz for frequency. Alright, so how can we produce emission spectra? I already kind of mentioned about that we can excite the atom, and so when we produce, right, so we can produce emission spectra like in this way. So we have what's called a discharge tube. So we'll have some gas in there, and inside this tube, it might be sodium gas or something like that. We'll then put a high voltage through that tube. That high voltage will make electrons jump up levels and then jump back down, and when they jump back down, you get these photons. So we put it through a thing called a spectroscope. So all a spectroscope does is that it splits the light into colours. And so when you look at that, what you'll see is some lines on there, and they're what we call a spectra. So those lines will be the colours related to the energy of the photon, but not HF, of course. So the colours related to the frequency. And so because each atom has particular energy levels, you'll have for each atom particular colours. So apply the voltage, excite the gas, and then when they drop to the lower level, a photon is produced. And so this is the kind of thing that you get. Alright, so here we go. Here's a couple of emission spectra. So the one on the top is hydrogen, and the one on the bottom is helium. There may be more lines than that, but these are the main ones. Alright, so the faint ones, there's some that would be not all that commonly occurring, so that they're not in there. So as you can see, there's particular colours for each of those. Again, relates to the energy levels of the atoms, and so that's what we would call an emission spectra. All right, and that's all right. So there's another spectra called the absorption spectra. And that's what happens when light gets absorbed. So the way that that's done is this. Alright, so we might have a light source here that's sending light in all directions, but we're just looking at to the right here. And then here is a cloud of gas in here. And so this light goes through the cloud of gas. So what this light could do is this light over here, what it could do is excite some electrons in atoms in this gas. So if that does that, what it's going to do is it's going to remove those colours relating to the difference in the energy level. And so that's what's the absorption spectra. So then we use our spectroscope, and so here we've got these lines. So these lines this time will be dark lines because those colours have been removed, and all the rest would be bright. And so again, there'll be particular, will depend on what the gas is, there'll be particular things. And this, both the emission and the absorption spectra are things that astronomers and cosmologists and that used when they were trying to find out, what stars and things are made of, or if there's a cloud of gas out there in the universe that they're looking at, what it's actually made from. Alright, here's another bit of a diagram. Alright, so here's hydrogen atom. So we got the emission spectra, so that's, as it shows here, when you've got atom excited and then they drop down. Alright, and here if it was excited to there and then dropping down. And so we've got these white lines, so it's all dark, and then we've got these lines of light. So all the black there, of course, is dark. Alright, so that's what an absorption spectra would be like. Emission spectra would be like. So B is the absorption spectra. So and you can see they're all down in their lower level, and then that could maybe get excited up to here, or it could get excited off altogether, or up to here. And so then you have these, because it's using that energy, so you have these lines here that are dark, and all the rest of it, the white bit, is light, whatever colour that might be. Alright. And this last bit, what it says is if you give more energy, so this is for the ionisation bit on the end here, if you get more energy than is needed to remove that electron, then it will come out with some kinetic energy. Alright, so that's kind of just a little bit about that, but what that is it's good evidence for the Bohr model of the atom. Alright, and so the Bohr model has to do with energy levels in the atom and that sort of thing. For atoms other than the hydrogen, which have got a lot more energy levels, a lot more electrons, it gets quite complicated, but the principle behind it's the same. Alright, so there's a bit of reading in your textbook there about the Bohr model. Talks a little bit about the Bohr model, and there's a set of problems for you to do, and then some revision for your assessment that you should have already know about on this topic of matter. As usual, there's some videos there associated with this topic, emission absorption spectra in particular, so you should make sure you watch those videos. And of course, things that you're not sure of, make sure you ask.